Hi, this is Peter with CalcBook, and today we're going to be looking at a steel member design, and in particular we're going to be looking at members with slender elements. This is going to be actually a two-part series, so the first part will be kind of the problem setup and background, and then we'll do the compression design, and then the second part of the series will be doing the flexure and combined loading, and then we'll also look at shear as well. So let's go ahead and get started and get into the compression design as well as the problem setup. Right, steel member design, we're going to be looking at a wide flange. We're going to be using the AISC spec, so it'll be Chapter E for compression, and then within Chapter E, we'll check for slender elements, and then we'll look at Chapter F for bending, and then we'll look at Chapter G for shear, and then Chapter H for combined loading. So first, we're going to take a look at Chapter E. So our problem statement for today is going to be to design a collector with an axial load and then loading applied in both axes, so about the strong and the weak axis. So we're going to have a beam length of 10 feet. We'll be looking at a W21 by 44. It's going to be A992 steel, and our loading is going to look like this. So we have an axial load of 145 kips due to earthquake. We have a vertical dead load in the X direction, or about the strong axis, of 350 pound per foot. A live load about the x-axis, 450 pound per foot. And then we have, in and out of the page here, you can't see it, is a horizontal load due to earthquake at 600 pound per foot. So maybe we have some equipment on the wall or a cladding or something like that that's going to put this wide flange into weak axis bending. And then along with collector design, right, there's a lot of sort of special seismic requirements. We are going to ignore that for now and just go ahead with these loads and use our AISC 7 loading combinations to design this member. So let's go ahead and open up CalcBook and we'll get started on the design. All right, we've got CalcBook open now, so we go ahead and click into our steel design. So we'll go ahead and use AISC 16th edition. Click into our member design, and then we'll be using a steel member. So to start for this part 1 series, we're just going to look at axial. We'll be looking at compression. So we'll go ahead and select our member. It's going to be a W shape, and we said it's a W21 by 44. So we'll scroll down here, select 21 by 44. All right, that's going to automatically pull up sort of the default values there for A992 steel, so we'll go ahead and leave that as is. And then we're going to be using the beam analysis and then our AISC 7 load combinations. So if we want, we can pop open the geometric properties that we're going to need, or we can jump right into the design. So for the beam loading, we're going to leave that right now because we'll be doing that for part 2. So we'll go ahead and click right into our axial design. Right, and we're going to go ahead and use compression, and we are going to enter in our unbraced length. So we're going to assume this is fully unbraced, the full length of the beam, which is 10 feet. So we have 10 feet in each direction, and we'll assume it's going to be pinned. And then our demand, right, we have a seismic load, axial load of 145 kips. So go ahead and enter that. Okay, so we are going to start off here with our load combination rate, which is just going to be the 1.2 dead plus earthquake, so 145 kips. Now this may update once we do our bending design, right, our strong axis and weak axis, right? It will ultimately decide the critical load combination based on the combined loading. So whatever the controlling load combination is for combined loading, it will make sure that all of these designs match that. But for now, it's showing load case 6, so we can check that once we do the remaining bending design calculations. So the first thing we want to do is check for slender elements. So we're going to check the flange, where we look at our width to thickness ratio for the flange and then our limiting width to thickness ratio, and we find that the flange is non-slender, so we're okay there. And then we go ahead and check our web, right, our width to thickness ratio, and we look at our web slenderness, and we are actually just slender. So we are going to have to utilize the Chapter E7 and look at potentially having to reduce the area of the section to account for that slenderness. So we can go ahead and open up the compressive strength section here. Right, we'll look at our slenderness ratio about each axis, about X and Y, and what our limiting is, right? That's going to be about the Y axis in this case. Calculate our elastic buckling stress. Right, since flexural torsional buckling is not being evaluated, we won't look at that, so it is controlled just by our elastic buckling stress, our flexural elastic buckling stress. And then we want to check on our effective area with slender elements. So we compare our width thickness against this controlling ratio here, and that decides whether or not we use E7-2, which would just be using the same area, the gross area of the element, or E7-3, which is a reduced area based on equation 7.3, and then there's a few other ones as well in there. So we do fall into that category. We have to look at reducing the area of the element. So we calculate our local buckling stress of the web, the elastic local buckling stress, and then we look at our effective width of that slender element using the reduction, right, which is based on equation E7-3. And then we calculate our effective area, right, which is going to be the gross area minus that reduction, and we're going to end up with 12.69 inches squared, which is pretty darn close to 13 inches squared, but we do have a slight reduction due to that slender element. So based on that reduced area, we can look at our compressive strength, which is going to come in at 294.26 kips. So that gives us a DC ratio of 0.49, right? So that's just the beginning part of the design where we're just looking at the compression, but we are going to come back in part 2 and look at the flexure and then the combined loading. So that was part 1 of a design with a member with slender elements, and we'll see you for part 2.